look at a massive high-voltage industrial robotic arm, the kind smashing heavy car chassis into place, and wonder, how is a tiny, fragile, 5-volt computer chip actually controlling that? I mean, we're talking about a processor that runs on less juice than a small flashlight, somehow bossing around heavy machinery. Well, welcome to our explainer. Today, we are absolutely pulling back the curtain on the technology behind this magic trick.
To really wrap our heads around this, we have to look at the massive gap that exists in almost every automated system out there. It's essentially brains versus brawn. On one side, you've got the brains, right? The microcontrollers and computer chips. They are incredibly smart, but physically, pretty weak. On the exact opposite side, you have the brawn, the heavy-duty electric motors that do all the literal heavy lifting. The problem is, the brains whisper in these tiny digital signals, but the brawn, it needs a megaphone of high voltage to actually get moving. So, what is that megaphone? It's a fascinating field of engineering called power electronics. Power electronics is the critical bridge connecting those low-power control signals from our microchips straight to the high-power systems driving the motors. It acts as the ultimate translator, making this whole connection possible using some very specialized semiconductor components, things you might have heard of, like MOSFETs and IGBTs. Honestly, without this bridge, our little microchip would literally fry in an instant if it tried to talk directly to an industrial motor. Here is our roadmap for this explainer. We'll start with the brains and the brawn, look at H-bridges, see how VFDs power massive AC motors, decode PWM, and then finally, tie the whole shebang together with a real-world robot. All right, let's dive right into Section 1, the brains and the brawn. Moving on to Section 2, H-bridges and directing the traffic. So, you have a basic DC motor, and you need to control its direction. You don't just want it to turn on, you want to make it spin forward and in reverse. To solve this, we use something called an H-bridge. Think of it like a circuit shaped like an H, with 4 strategically placed electronic switches. By selectively opening and closing these switches in diagonal pairs, we can completely dictate the path the electricity takes. It's brilliant in its simplicity. First, you activate one set of diagonal switches, and the current flows, let's say, to the right. That spins the motor forward. To reverse it, you just turn those off and activate the opposite diagonal pair, forcing the current to flow to the left. You can actually see this flow in action right here on the screen. Look down at the bottom left. The top left and bottom right switches are closed. The current, shown by those arrows, flows down and to the right through the motor in the center. Bam, that's your forward state. Now look at the bottom right, where we flip the script. The top right and bottom left switches are now closed, and the current flows down and to the left. It acts exactly like directing traffic. You're seamlessly reversing the motor's physical rotation, and you never even had to touch or change the main power supply. Section 3. VFDs, or powering AC motors. Now, while H-bridges are totally great for those basic DC motors, the kind you'd find in toys or smaller electronics, modern industry relies on massive AC motors. We're talking the ones that run giant conveyor belts, municipal water pumps, and huge factory lines. To control the speed and power of those heavy-duty AC beasts, we need something beefier, variable frequency drives, or VFDs. A VFD is basically a 3-stage power conversion factory. Stage 1 is the rectifier. It grabs standard AC wall power and flattens it out into DC power. Stage 2 is the DC link, which uses capacitors to store and smooth out that energy, kind of like a holding reservoir. And finally, Stage 3 is the inverter, which grabs that stored DC power and chops it back up into a brand new, highly customized AC signal. If you follow this block diagram, you can see that 3-stage process perfectly. Standard AC power comes rushing in on the left. It gets flattened by the rectifier, hangs out in the DC link in the middle, and then hits the inverter on the right. By tweaking the exact frequency of that final AC output leaving the inverter, we gain incredibly precise control over exactly how fast that massive industrial motor spins. The absolute crucial part here is how that final inverter stage actually pulls off the illusion of creating a fake AC wave at a flat DC power. Remember those power electronic components we mentioned earlier, the MOSFETs and IGBTs? This is where they shine. They act as heavy-duty, ultra-high-speed electronic switches. By rapidly turning these switches on and off, literally thousands of times a second, in highly specific patterns, the inverter easily synthesizes an alternating current that the motor can actually use. Which brings us to Section 4, PWM, the language of control. So, question. How does our tiny microcontroller brain tell those massive switches to flip thousands of times a second? It speaks to them using a language called pulse width modulation, or PWM for short. PWM is super fascinating because it really highlights the friction between the digital world and the physical world. See, the microcontroller can only output blocky, rigid digital signals. It is either entirely on with 5 volts or totally off with 0 volts, no in between. But the motor? It demands a smooth, analog, continuous flow of energy to physically rotate without jerking around. PWM bridges this gap by rapidly pulsing those on and off signals. By changing how wide the on pulse is compared to the off time, it effectively tricks the motor into experiencing a lower average voltage. Take a look at this simulation graph. It proves the concept perfectly. Notice those tall, sharp blue lines? That's the actual PWM voltage signal. It's harsh, it's blocky, it's strictly on and off. But then look at the orange line, which represents the actual current flowing through the motor. It's surprisingly smooth. Why? Because the physical copper coils inside the motor possess a natural property called inductance. Think of inductance as a built-in shock absorber. It physically smooths out those harsh digital voltage pulses into a nice, steady, continuous current.
Finally, Section 5, Real-World Robot Control. Let's pull all this theory out of the clouds and put it into practice with something tangible. Here, an Arduino microcontroller is acting as our brain. It's wired right into that red board, which is an L298N motor driver shield. That shield houses our H-bridges, our power electronics bridge. And right beside it, you can see how this all mounts onto a small mobile robot chassis. The battery pack provides the raw brawn, the Arduino provides the brains, and that red shield translates between the two so nothing blows up.
So just to summarize how this works in a real robot. The Arduino uses the language of PWM to control the effective voltage, meaning it can tell the robot to speed up or slow down smoothly. It uses the H-bridge on the red shield to reverse the current, which lets the robot back up. And because it can control the left and right wheels entirely independently, it can spin one forward and one backward to turn on a dime. That's a concept called differential turning. Best of all, the whole ride stays smooth because the motor's physical inductance absorbs all those harsh digital signals. We've just seen how a tiny 5-volt chip directs a small desktop robot. But I want to leave you with this final, kind of mind-blowing thought. The exact same principles we just talked about, PWM, H-bridges, and VFDs, they don't just apply to desktop toys. These are the exact same fundamental concepts used to drive massive industrial assembly lines and the electric vehicles passing you on the highway every single day. The computer chips stay small, but the power electronics simply scale up to handle the massive load. Think about that the next time you see a giant robotic arm in action or an EV accelerating off the line. Thanks for joining me on this explainer, and keep questioning how the amazing machinery around you actually works.